So welcome to eSpace. It's a new lecture on sequential circuits. So in this lecture is part 5 of the sequential circuits. So in this lecture we will be dealing about design procedure of asynchronous sequential circuit, reduction of state and flow tables, prime implication table, same part of it, and race free state assignment. It has two methods are there. One is shared row method and one is multiple row method. So let us see the design procedure of asynchronous sequential circuit. So it starts from the statement of the problem and results in a logic diagram. Logic diagram means the data circuit involving gates. Here there will be no flip-flop, no clock. So it will be gates only or the latches with the latches. Yes, these are the steps. A primitive flow table is obtained from the design specifications from the state table or the state diagram. A primitive flow table is generated, is obtained. The flow table is reduced to minimum number of states. Then states are given binary assignment, and that should be race free. From the transition table, we derive the logic diagram as a common circuit with feedback, that is a gates with feedback, or as a circuit with latches, SR latches. The entire process will be demonstrated by going through a specific example. So this is an example to design a gated latch circuit with two inputs, gate G and D data, and one output Q. Binary information, then this is a logic here. Binary information present as D input is transferred to Q when G is equal to 1. So when there are two inputs G and D, when G is equal to 1, whatever value comes at the D is transferred to Q. The Q output will follow the D input as long as G is equal to 1. The same thing. When G goes to 0, the output remains in the same state even if D changes its value. So when G is equal to 0, whatever value at the Q, it is maintained, and it does not depend upon the value of D. So in summary, the gated latch is a memory element that accepts the value of D when G is equal to 1 and retains this value after G goes to 0, and change in D does not change the value of the output Q. Why it is called memory element means when G goes to 0, whatever value at the Q is retained, it is remembered. So that's why it is called a memory element. And this is the problem diagram. There are two inputs D and G. This is a G and the D and the Q. And so you have to find the internal circuitry of the this block diagram. So this is a state table. There are 6 states, that's A, B, C, D, A, and F. And these are 3 inputs. So whenever 3 inputs, these are 2 inputs, and whenever G is equal to 1, whatever value is the D is transferred here. So it is D on here. D is equal to Q because G is equal to 1. D is equal to Q because G is equal to 1. And when in the state C, when it is 0, 0, suppose it is the value of 0. So value of G is 0. So whatever value is there in the Q, it is maintained here. So this can be obtained after state A or D. That is when it is 0, 1, it is 0, and 1, 0, it is 0. This 0 is same state is maintained here. Same value is maintained here. And this one E, and when it is D is equal to 1 and G is equal to 0, this comes after B or F. So it is in this B state, when G goes to 0, this value of 1 is retained here. So that is given here. And again B, when it goes to 1, when it goes to 0, whatever state in the Q is maintained here. That is why it is 1. And after state E, it is 1, 0 and 0, 0. So when this after D goes to 0, whatever this output was previously equal to 1. So this is after state F. In F state F, this value of 1 is maintained here. Okay. So this is a primitive. We have to generate a primitive flow table from the state table. So first we will see state A. So first you will see state A. And one more thing. The state transitions are from 0, 1 to 0, 0 or to 1 0. Only these transitions are allowed here. Again, another possibility here, this is 1 1 changes to 1 0, and this changes to 0 0, and 0 0 to 1 1 is not allowed. Again, 0 1 to 1 1 0 1 0 is not allowed. So let us take the state A here. So when at the state A, when the inputs are 0 1, it remains in the same state. So this is the stable state when A is equal to, and when the inputs are 0 1, it remains in the same state and the output is 0. This is a stable state. It is marked with the circle. And I earlier I told you this from 0 1 it cannot go to 1 0. So that state is invalid here. So it is given by both dash. So now let us see when inputs are at the state A, when input is 0 0, the input goes from the input at the state A, it is input are 1 0 1, and when it goes to 0 0, what happens here? D is 0 1, G goes to 1 to 0. So according to the problem statement, whatever value at 0 it was at 0, output was 0. Whatever value the output is maintained here, so it is 0 0. So we have here 0 0 0 0 0 means the state C comma 0, C comma dash. It is the values 0 0 0. That's why it's a transition state. That's why it is given as dash here. Now let us see when it goes from 0 1, this is a state A. When it goes to 1 1, when the input goes to 1 1, it's 1 here. So when G is equal to 1, whatever value the D is come here, value is 1. But this is a transition state. That's why they will give a dash at the output. So it is this 1 1. This goes to 1 1 1 here. So the state is B. So here it is B comma dash. Now let us take B. Now let us take B here. B state is given by 1 1 and output 1. So one possibility is that it goes to the same state, that is B, and the output is 1. So that is the stable state here, that is B comma 1, and the unallowed state is 0 0. So it is given by dash. Now let us see the next states. When 1 1 when the inputs are 1 1, then it goes to 0 1, and the inputs goes to 0 1. This is 1 here. When G is equal to 1, output Q is equal to D. So it is 0 0 1 0. That is what you have to see the state. So it is A here. So it will go to A comma hash, A comma dash. Now again let us see. Inputs are 1 1. This is the B state, and then it goes to 1 0. So it is 0 here. Whatever value the output is maintained here. So output is 1. So I have to see the which state is here. 1 0 1. It is 1 0 1. It is state E. So E comma dash. Now let us take C here. C is 0 0. So again, and it is 0. This is 0 0. It remains in the same state, that is a stable state C, and output 0. it is C comma here, so it's a stable state. So and this is 0, C is state is 0 0, and unallowed state is 1 1. So that will be given by a dash dash. It is here and a dash dash. And then let us see the other combinations. 0 0 comma 0. This is the C state, and when it goes to 0 1, what is the value of output? When G is equal to 1, output is equal to D, that is it is 0. So let us see which state is that. That is 0 1 0. That is A state. State A. I give A comma hash A comma dash, and then next state is 0 0 0. The state C, and then it other combination is when it goes to 1 0. So that is when G is equal to 0. The state is maintained here, so it is 0. So let us see what this state is here. It is D state. So D comma hash C comma dash. So next state is at the next state D. Again stable state is, so D is 1 0. The stable state is 1 0 1 0 0. So D comma 0. This is stable state D comma 0. Output is 0. And then next unallowed state is 1 0. Sorry, 1 0 means 0 1. So let us see here, that will be given by both dash. Let's don't care. And now let us see here, D is 1 0 0, and the next transition is allowed transition combination is 0 0. G is equal to 0, so and Q is equal to 0, so it is 0. So 1 0 to 0 0 0, that is state C. And next see next transition 1 0 to 1 1 1 1 1. So when G is equal to 1, whatever value comes at D, it is going to Q. So it is 1 here. So 1 1 1 is B. So B comma dash. So next we'll take E. So E 1 0 1. So this 1 0, this 1 0, whatever 1 0, the stable state becomes A here. E, it's stable state. And unallowed transition is 0 1. So here we'll put a dash dash. And now let us see other combinations. So one is defined by 1 0 1. So next transition is 0 0. So G is equal to 0. Output was earlier output was Q, so it will come here. So you'll see the transition. So it is 0 0 1 F. So again we'll see the next transition. It is 1 1. So because G is equal to 1, Q is equal to 1, D, then because D is equal to 1, so D is transferred to Q. So we'll see the transfer 1 1 1 means it is B. So B state is B, B comma dash. Now let us take F. F again 0 0 1. So when the inputs are 0 0, it will remain the same state, stable state. So F1, and then the unallowed transitions are 1 1. So at 1 1 we'll put both two dashes. So now let us see the combinations for transition. So 0 0 1, this is the F state. So it will be the one transition is like this. So 0 1. So it is 1. But because G is equal to 1, so when G is equal to 1, because D is equal to 0, so Q is equal to 0. So we'll see the table here. 0 1 0, that is A. So this state A. So again 0 0 1. Next possible transition is 1 0 G value 0. So whatever values it at 1 is transferred here. Whatever values the previous value is maintained here. So 101. See, so we look at we can look at the table. So 101, that is E. So E dash. So we have finished filling the primitive flow table. So we earlier. So this was the table A B C D E F. So here you can see. So we can merge this. We can split this table into two. So here you can see these are common. C A C A C D. A state here. So you can see here C D. You can see here these three rows are equivalent or it has similar values, and B E F the similar values again. So we can split this table into two. One is with A C D and another one is B E F. So yeah, split the table and then combined into two. So ACD combined into two. See here. So you can see here the ACD. This I have merged into one. So again merged into one and then combined. So that is, so we can have this. We can have just two states because they are all equivalent. It's a new modified table. So now let us derive the output. So here you can see here. These are the output. This is the output. Value of output 0 1 0 0 0 1, and these are the states. This is from 0 to 0, 0 to 0, 0 to 1, 0 to 0, 0 to 1 to 1, 1 to 0, 1 to 1, and 1 to 1. And I have made a table here. You can derive from the K map. You can derive Y. So first is 0. So you can see here 0 to 0. First is 0 to 0, 0, 0. The state value A, this value of state A is 0, B is 1. So here it will come 1 0 0 1 0 0 0 1 0, and here this 1 1 0 1 1 1 0 1 1. So we can derive according to the combiner circuit from the K map. We can get the output equation as like this: Y as a function of small y and dg. Can get the y output capital Y here, dg plus g bar y, and q is equal to y. You can see here this is a don't care here. So you can derive that y is equal to q, and so this is a logic diagram. So you can see here y is equal to dg plus g bar y. So that's the circuit here. So this is a required circuit logic diagram, and with circuit is SR latch. Suppose we can make the same Boolean function with made up of SR latch. So here you can see here this is small y and this is a capital Y. 0 to 0 transition. You can see here S is equal to 0, R is equal to X. 0 to 0, 0 0, 0 to 1, 1 0, 0 to 0, 0 x, 1 to 1, x 0, 1 to 0, 0 1, 1 to 1, x 0, 1 to 1, x 0. So you can equate S as S is equal to dg and R is equal to d bar g. So this is a logic diagram made up of latch. The same circuit shown before is made up of latches. It's made up of SR latch. So actually it is a D latch here. So the gated latch acts as a D latch here. This is actually a D latch. So next we see reduction of state table. Suppose we have a state table here. We can reduce it to small number. Suppose we have a state of 7. We have a circuit of 7 state variables. We can reduce it to 4 or 5, and we can reduce the circuit complexity. So The reduction of state table, the procedure of reducing the number of internal states in asynchronous circuit is similar to that of synchronous circuit. So we have earlier studied with the reduction of state table for synchronous circuit. This is for asynchronous circuit. The algorithm used for synchronous circuit will be applied to asynchronous circuits here. We'll be using the implication table and merge diagram for reduction. The state table to be reduced is given in the next slide. So you can see here. This is the state table to reduced. So there are totally 7 state, 1 input and 1 output. So with the state table, look at it. So we'll be finding the equivalent states and reducing the state table with the help of a implication table called implication table. What is implication? We have studied before. So again, I will be dealing with the implication table again in the for the asynchronous circuits. So the drawing of an implication table is simple. On the left side along the vertical are listed all the state defined in the state table except the first. So here we have A, B, C, D, E, F, G. So we will be writing B, C, D, E, F, G at the vertical side along the left side. On the bottom we will be listing all state except the last. So that is A, B, C, D, E, F. The two states having different outputs for the same inputs are not equivalent states. So two states having different outputs are not equivalent states, and these are marked as X. And equivalent states with two states which having same output is marked as tick. So let us see here. So this is implication as we discussed earlier. This is B, C, D, E, F, G and A, B, C, D, E, F at the horizontal side and the vertical side. So this is a state table. So let us first take the from the horizontal axis. So let us first take the pair AB. So first is here it is AB. See a state A and B have the same output, so they are equivalent state, and difference between them is D and D. So when D and D are equivalent states, then A and B are also equivalent. So you'll be writing like this because the outputs are equal. You'll be giving with the tick mark and then to write the state D. When D are equal, then A and B are equal. Now A and C, they are not equal. So we'll be putting it the cross. Then AD you can see here again, that is outputs are different, so it is not equivalent state. A and D again, it is not equivalent state. You can see here it's not equivalent state. A and F, C, C, B, both are not outputs are equal, but the CD again, see here CD the CD, when CD are no equal, it will be equal, but so it is CD and C and D are not equal, so it is written as not equal state. A and G, you can see here different output, so it is not equal. BC not equal. BD not equal. BE again not equal. BG again not equal. CD, can see here CD, they are not equal. That's why it is this A and F are not equal. C and D are not equal. C and E, again you can see C and E not equal. C and F not equal. You can see D and E, you can see here D and E, see you can see the same output and same next state, so they are equal. We will be putting a tick mark here there. D and E, D and F not equal. D and G, you can see here D and G, a same output, difference are that D and when D and E are equal, then D and G are equal. So it is. So here put a tick mark when D and DE are equal, then D and G is also equal. Now let us see E and F. E and F not equal. E and G. E and G. E and G. Same output. The condition is that when D and D are equal, then E and G is also equal. So we'll put a tick mark here and with respect to D and D, and F and G not equal. So this is the implication table we have got here. So we have got 1, 2, 3, 4 equivalent states, 4 equivalent pair, that is AB, DE, DG and EG. So this is here. So according to implication that the equivalent states are AB, DE, DG and EG. You can see here. So now the next step is using a merger diagram. So with merger diagram we can find out which are the compatible pair, that is which are the equivalent pair with the reduced number of states. The merger diagram is a graph in which each state is represented by a dot placing along the circumference of a circle. So we will be representing all the states, that is A, B, C, D, E, F, G on the circumference of a circle, and lines are drawn between two dots between any two dots to form a compatible pair. So the equivalent states are drawn by a the dots are joined by a line, and a triangle represents a compatible with 3 states. In general, n-sided polygon represents a compatible n states. So let us see, well, when you see that you will understand. So these are the equivalent states. These are all the states A, B, C, D, E, F, G are put on the circumference of a circle. These are the equivalent states A, B. So we'll be drawing A, B here, then D, E here, D, E here, D, G and E, G. We'll be joining all these four pairs. So let us see here. A, B joined, D, E, D, G and E, G. So let us see here. So the compatible pair means this can be combined into one state. This is one state, and these three can be combined into one state, and this as one state. So the maximum, it is called as maximum compatibles. So it is shown here A, B, C, D, E and F. And now you can see here. So these 4 pairs can be reduced into 4 states. So we are reducing the 7 states into 4 states. So here reduced states are A, C, D, F. So I am putting A for A and B pair, C for C, D for DEG, DEC, DEG compatible pair, and then F for F. So this is the reduced state table with ACDF. I just replace those values with the previous values, previous value with the new values. ACDF can be so again this can be further simplified into 4 states ACDF. So that is here, this ACDF and shown here. Now we have got only 4 states. So final simplification, we have been successful in reducing 7 states to 4. This can reduce a great level of circuit complexity, that we can reduce many of gates and latches. We can reduce a big amount of circuit complexity. So this is a reduced state table. So this is a reduced state table. So next we'll see in the race-free state assignment. So in the last lecture we have seen the races, that is critical race and non-critical races. Non-critical races can be it is not a big issue, but we should not have critical races. Critical races make a synchronous circuit fail. So once a reduced flow table is derived from the next flow table derived, then the next step in the design is to assign binary variables to each stable state. The prime objective in choosing a proper binary state is the prevention of critical race. By assigning proper state assignment, we can prevent critical races. Critical races makes a asynchronous circuit fail. So we can avoid critical races by providing a good state assignment. Critical races can be avoided by making a binary state in such a way that only one variable changes at any given time when a state transition occurs in the flow table. So in order to achieve this transition must occur between adjacent assignments. So there are two methods of state assignment. One is shared row method. This is much more efficient one, shared row method, and another one is multiple row method, that is uh, comparatively relatively easier. So we'll see the two methods, shared row method and multiple row method. So this is an example flow table in which we have to give a race free state assignment. So there are four states. You can see here from A, when the input is 0, it goes to state B, and when it is 0, 1, it remains in the same state, that is a stable state. The circle one are stable state, and when from A, when input is 1, 1, it goes to state D. So when the input is 1, 0, it remains in the same state A. So similarly, you can see the next rows. So just see it. So first we will do the shared row method. So first we have to make a transition diagram. That is, whichever states the transition happens, we have to draw a transition diagram for that. So this is the given flow table here. So this is a transition diagram. So see here, there are four states. So I have drawn four dots at the four states: 0, 0, 0, 1, 1, 1, 1, 0. That is A, B, C, D. So let us now, according to the flow table, we have to draw the transition diagram. So when it is state A, it is going to state B. So it is the transition. There's a transition between A to B. So that is shown here, A to B. Then A to A. So it's not we does not bother that. Next is A to D. So here A to D transition, and then here this B to B. So it is now. So yeah, that is, we cannot. Don't care here. B to D is a transition. So it is B to D. Then B to B is the same state. Then B to A. So here you can see. Then C to C, and then C to A. Then C to B. Then C to C, same state. Then D to C, D to C, D to D, D to D, and D to C. So these are the transitions. Now we have to see the transition where there are only one variable change. It only that should be allowed. So A to B transition 0 to 0, 1, there is only one variable change. So it is allowed here. Then B to C, you can see there is one variable change, it is allowed. D to C, that's also allowed. But C to A, that is, there are two variables change, so that is not allowed here. Then B to D, that's also two variable change, so these two transition is not allowed. So can cross that two transitions. Now let us make a method to find a race free. So here there are critical races here, so we have to make a race free assignment. So take a K map and enter the states in T shape. So A, B, C, D. I have written the T states here. Now again, let us see the transitions according to the flow table. First is A to B. A to B. So A to B, that is allowed here. So let us see here. So this I have assignments. These are 0, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, same shape. So let us see the flow table here. A to B. A to B are adjacent, so there is no issue. And A to A is again the same state. A to D. So here you can see it is a two variable change transition. So we have to make an intermediate state here, and the transition should happen this way. So that is, I'll show here 1 minute. Let me take the pen. So we have to give a transition like this. So E. We have to make a transition through E. A to D through a transition E. So that is the point. So B, when for state B, B to B, no issue. B to D, it is adjacent. B to B again. B to A, no problem. C, C to C, C to A, C A. See here, C to A, it is not adjacent. So we have to make a adjustment here. This is a intermediate transition like this to go like this. So we have to make a new state F here with 0, 1, 0, and the transition should happen through F. So that is C to A. Yes, C to A. Then C to B, that is adjacent, no issue. Again D, D to C. So here again that is not adjacent. So we have to make a intermediate transition like this. We have to make a transition. We have to make a new state G, 1, 1, 1, and D should go through G and go to C. So again D to D, D to D, no issue. Again D to C, again the same solution is done here. So I'll make the new table. So it came up like this. So here you can see here. So A to D transition is done through E, D to C transition is done through G, and C to A through F. So again we'll be drawing a new transition diagram. So A to B, so these are the new values: 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1. So again there is a float as a 1. This is the previous one, A to B. So A to D is given through a new intermediate state E. Can see here to D. So we have a new state here 1, 0, 0. Then the transition B to A, then B to D, B to C, and then C to A. We have to give through a new intermediate state F, that is 0, 1, 0. New state F here, intermediate state. Then again C to D is given through G, that is G is 1, 1, 1, new state. C to D transition is given through here. Now it is this because this variable change, one single variable change, the B to D is possible now, but the C to D is not possible now. So this we have made a new intermediate state G here. So D to G and D to G and G to C. So this is a new transition diagram. So with this two transition diagram came up, we can draw the new modified flow table. This is a new modified flow table. These are the states 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1, and A, B, C, D, and this new two states F and G is also added to the modified flow table, and these are the inputs 0, 0, 0, 1, 1, 1, 1, 0, and this is the previous given flow table. And now let us fill up the modified flow table. So first is A to B, so that is not an issue. A to B, okay, and A to A, the stable state A to D, and you can see here A to D is passing through E. So here we will be writing E, and then for E here, for value 1, 1, it is D. So here it is D. And next, this state is A, stable state, no change for that. Then B to B, again stable state. B to D, see here B to D, it is possible, that is even. and B to B again stable state, and then B to A again, that is also allowed. Then state C to C is allowed here. Then C to A, see here C to A. So there's an intermediate state here, and is F, and F at the same, for same input value it will be A. So here A comes here, and C again C to B. That is no issue. Same state, same transition, and C to C, same, that's stable state, same transition, and F and D is over. Now we'll take D. So D to A. Sorry, here D to C. See here D to C. D to C, there's independent transition G, and G for the same value there will be C. So C comes here, and see here D for D same, D for D same, and D to C again G, and for G for the same input C will come there. So this is the modified flow table. All other are given, don't care, and we have put a dash, and there's a one state I haven't drawn. That is also that for that all the four values are don't care. That is the state 110 is not shown here, and for that there are the four values are also don't care. So this is a modified flow table. This is a race free state assignment. There will be no critical races here. So that's it. So let us see the multiple row method. The earlier method was a little bit difficult for when the state variable increases to more number of values, more number, the reducing the flow table to a race free state assignment is difficult. This is a multiple row method. In this is much more simple, but this is not efficient as that of shared row method. So first we form a table where each state in the original flow table is replaced by two or more combinations of state variables. So there are two binary state variables for each stable state, each being the logical complement of each. That is one's complement you are taking of each state variable and write in a K map. So here we have four states. So we are making the copies of each state. So there will be 8 total state. Totally there will be 8 states. So here I am writing A1, B1, C1, D1, and for A1 we will be writing a new state A2, which is the logical complement of the previous state. That is A1. If A1 equal to 0, 0, 0, we'll write a new state A2 as logical, which is logical complement of the A1, that is 1, 1, 1 here. See here. And for B, see for B1 it is 0, 0, 1. So B2 it is 1, 1, 0. So like that we are writing A2, B2, C2 and D2. So let us now write a modified the final flow table without using transition diagram directly, right? So here we have state that states included in the K map A1, A2, B1, B2, C1, C2, D1, D2. So there are totally 8 states. So here, as I already told, A2 is the logical complement of A1. B2 is a logical complement of B2 is a logical complement of B1, that is 0, 0, 1, 2, 1, 1, 0. So like here C2 and C1, D2 and D1. So let us now fill the final flow table with respect to the earlier flow table here. So here you see A1, you will write A1 here. A1 for 0, 0, this is the input. For 0, 0 input, it is going to B1. So let us see whether it is adjacent or not. A1 and B1 are adjacent. So it is allowed. So here it is B1, you can write B1. A1 and A1, the stable state A1, D1. See here, so here you can see A1 and D1 are again just it is adjacent. A1 and D1 are adjacent. Can write it is allowed here. So D1 and A1 and A1 stable state again it is allowed. Now it is A2 to B2. So here you can see A2 to B2 is adjacent, it is allowed, and A2 to A2 and A2 again it is allowed. A2 to D2, sorry, yeah, A2 to D2 it is allowed. A2 to D2 is adjacent, it is allowed, and again A2 and A2 stable state. Okay, now let us fill here B1 B1 to B1 allowed, stable state is allowed here. B1 to D1, see here B1 to D1, so it is not adjacent, we have to take B1 and D2 here. So here it is D2, so D2. Now again B1 to B1 it is stable state, B1 to A1 it is adjacent, it is allowed, and again B2 to B2 allowed, B2 to D2, B2 to D2, so it is not adjacent. B2 to D2 it is not adjacent, you have to take B2 to D1, so it is D1 here. And now again B2 to B2 allowed, B2 to A2 allowed, C1 to C1 allowed, C1 to A1, C1 and A1, see here C1 and A1 it is not adjacent, so it's here to take C1 to A2 here, C1 and B1, C1 and B1 allowed, it is adjacent, allowed, C1 and C1 again it is allowed, C2 to C2 allowed, C2 to A2, C2 to A2, see here C2 to A2 is not adjacent, so we have to take A1, it's A1 here. Then now again C2 to B2, C2 to B2 is adjacent, you have to take, it is allowed, C2 to C2 again is a stable state. Now last one D1 to C1, D1 to C1 allowed, adjacent, D1 to D1 stable state, again D1 to D1 stable state, D1 to C1, D1 to C1 allowed, adjacent, it is allowed. Again now take D2 to C2, D2 to C2 adjacent, it is allowed, D2 to D2, D2 to D2, again D2 to C2, D2 to C2 allowed. So this is the final flow table, modified flow table without critical races. But the number of states are more than the previous method. This is not that's efficient, but it is a very easy method. Suppose we are having more number of states, from 16, 30 states, we can do this method. This is much more easier. So that's it. Please like and share the video, subscribe the channel. If you have any comments, mail me to chanch484@gmail.com or put at the comment section. Thank you. See you in the next lecture.